So we will study some properties of charge conjugation matrix today. Now, this first property is that we know that charge conjugation matrix satisfies this relation by the very definition. Therefore, from this you can show that C inverse gamma 5C is gamma 5 transpose. Using this relation, you can show that. This is an exercise, but you can show that directly because it is simple. C inverse gamma 5C is you write down gamma 5 opening up this definition like this way, product of gamma matrices, and in between each pair of gamma matrices you introduce this identity matrix here, and now you couple these first three, this will give according to this equation. This is true for all mu's, so gamma 0 gamma 1 for all mu's. Therefore this will give you minus gamma 0 t. The other next term will give you minus gamma 1 t, like this. Okay, so you get 4 terms. Now all the 4 minus signs will give you this minus 1 to the power 4, which is 1, and this rest is this. Now you can make this whole transpose. If you make this whole transpose, then the matrices should be taken in the reverse order, because A B whole transpose is B transpose A transpose. Okay, because of this. Now in this, inside this bracket, inside this transposition, what you do, you want to have gamma 5. Therefore it should be like gamma 0 gamma 1 gamma 2 gamma 3. So you have to bring this in front first, and to bring this in front you have to exchange with 3 gamma matrices, and gamma 0 anti-commutes with all gamma matrices, gamma 1 gamma 2 gamma 3. It commutes with itself, but it anti-commutes with all other gamma matrices. Therefore when you skip it, bring it to the front 3 times, you have to take the anti-commutation relation, though 3 minus signs will come. So gamma 0 will come in front. At the next step, gamma 1 has to be brought after gamma 0. Therefore you have to jump twice. Therefore 2 minus signs will come because of the anti-commutation relation between gamma 1 gamma 2 and gamma 1 gamma 3. And likewise, after doing that, gamma 2 have to come here. Therefore you have 1 extra minus sign. So you have 6 minus signs here, which gives you minus 1 to the power 6 is 1. Therefore you get this term, which is basically gamma transpose. Okay, so we proved that this equation. Clear? So this is, C also satisfies this equation by virtue of this equation. All right.
Yes, sir.
At least in the middles, sometimes say yes sir or no sir. Otherwise I will not be aware that you are there or not. Okay. Now there is another interesting property, which is that this matrix C has to be antisymmetric. Let us prove this. To prove this, we have to use the fact that when a field is charge conjugated twice, it gives the same field, because charge conjugation implies making all the particles represented by the field to its antiparticles. And again, charge conjugation means reverting back the antiparticles to their particles. Therefore, by this notation, charge conjugation of this field psi C, its charge conjugation again will give you the original field psi. Okay, you can use this identity transformation. This is an identity transformation, twice charge conjugation. You can see that C is antisymmetric if this has to follow. To show this, let's do this. We know that psi C is this object. Okay, write down psi C, where C satisfies this. Now, before evaluating the left hand side, try to find out what is psi bar C. Now, psi bar C by definition is psi C dagger gamma 0. Now, psi C dagger is the dagger of this whole thing into gamma 0. Now, once you take the dagger, individual parts will be daggered, but in the reverse order. Okay. Therefore, psi star dagger, gamma 0 transpose dagger, C dagger, then this gamma 0 is there. Now, psi star dagger is psi transpose, because dagger is star into transpose, so 2 stars makes psi and transpose remains. So this is psi transpose. Gamma 0, we keep this as this, and C being a unitary matrix, we have shown C dagger I can write also like C inverse gamma 0. Clear? So psi C bar is this. Now we can simplify this utilizing this equation, which is the equation identity which C satisfies. If you use this for mu equal to 0, this gives you this. Okay. And therefore C inverse gamma 0, which is lying here, C inverse gamma 0 from this equation you can write as minus gamma 0 t into C inverse, where you have right multiplied by C inverse. Okay. Therefore, in place of C inverse gamma 0, you can put this. So from this equation, we again come back to this equation. Psi C bar is this expression. In place of C inverse gamma 0, you replace it by this term. Okay. Now, this is minus, this minus comes front, psi transpose gamma 0 dagger transpose, psi gamma 0 transpose C inverse. Now, you take this, this is gamma 0 dagger gamma 0 transpose, so which is gamma 0 dagger whole transpose. So A transpose B transpose equal to BA whole transpose, that we have used. Now, gamma 0 dagger is gamma 0, therefore gamma 0 square is 1, so this term will go. So you are left with minus psi transpose this. So psi bar t, so psi C bar will be related to psi by this equation. So there are two equations. Psi C is related to psi by this equation, and its psi C bar is related to psi by this equation. One is related to psi star, other is related to psi transpose. Okay. Now with these two equations, we can now find out what is this. Now this means first write psi C here and then write whole C. The second C I write here. Now C gamma 0 t, psi star again is psi dagger transpose, because the obvious reason, it is star transpose. So it is, so this is this. Just stop me if you can't follow. Okay. Now just a minute. Now, these two terms can be put together as this whole transpose, thus changing the order. Okay, so you have, and these two will give you psi bar and whole transpose. Therefore, this will give you this. Okay, clear? Now we have shown that psi bar C is this, just in this last slide we have shown this. Therefore, here we can make the transpose of this to get its whole transpose, which is C inverse transpose, psi transpose transpose. Okay, and which is this, because psi transpose transpose is psi, so we put this in place of this to get this equation or this equation. Clear?
Yes, sir.
These are normal steps you can, but you have to do yourself. Don't just look at the notes later. Just work out in hand. Otherwise, you will not get confidence. Now the requirement that psi C should be psi, that means this should be psi, means the whole thing should be identity. Clear? This thing should be identity, because which means this. Okay. Now you can use this relation, this standard identity. C inverse is 1 for all matrices. So take its transpose. So you get this equation. Okay, C transpose, C inverse transpose. Now this is identity. This is also identity. So you can put them equal. So both are equal to identity. This and this. The left-hand side of these two equations are both equal to identity. From this you can easily get, just do some, you can cancel this term, cancel this matrix, or cancel this matrix means multiply both sides on the left by the inverse of this matrix to get C equal to minus C transpose, which is basically the fact that C is antisymmetric, because then Cij is minus Cji, okay, because of this transpose, which is C is antisymmetric. So the matrix C we introduced as a charge conjugation transformation of this Dirac field is antisymmetric. It has to be antisymmetric. So when we will construct this matrix, you have to be careful that it should be antisymmetric. Those are thumb rules which you can look at before checking other identities satisfied by C. It has to be antisymmetric. Clear? Now let's proceed. Just a minute. Now we will study an important, very important aspect of Dirac field and charge conjugation, which is how the Dirac bilinears transform under charge conjugation. Now you know, all of you know what are Dirac bilinears, because for the case of parity we have done this. Now note this, since Lagrangians are always Lorentz invariant, whenever we have to write down any Lagrangian, not necessarily free Lagrangian we have already written down, but in the next step, which we will come forward soon, in the next step, we have to write the Lagrangians which will represent interactions of different particles, quarks, baryons, mesons, etc. Now, whatever be the interaction part of these Lagrangians, they are related to any physical processes, but the thing is that the interaction Lagrangian, being a Lagrangian, it should be Lorentz invariant, and therefore, if this Lagrangian should contain Dirac field, it must appear in this form, because you have to make Lagrangian invariant. So psi has a particular way of transformation under Lorentz transformation, which is psi goes to a matrix into psi. But when you have to construct something out of psi which will not be Lorentz invariant, then that S should be cancelled, and that S can be cancelled by psi bar only, because we all know that in psi bar, psi is a Lorentz invariant term. In that case, F is 1. Okay. Therefore, so this is the most general form of appearance of the Dirac fields in the Lagrangian, so as to make it make Lagrangian Lorentz invariant objects. And also this object, which is F is a 4x4 matrix, psi 1 is a 1x4 matrix, psi 2 is a 4x1 column vector. Therefore, this whole thing should be an 1x1, and Lagrangian should be like that. For that reason also, one requires this kind of terms. If Dirac fields are there, this kind of term should be there in the Lagrangian involving Dirac fields. It is not that this is the only term. It can be multiplied by other terms like a mu or phi, etc. But we have to, whenever we have to introduce Dirac fields in the Lagrangian, we can intuitively say that the form of the Dirac fields appearance in the Lagrangian must be like this in this box. Is it clear? Moreover, it is not this object, so see, F is a 4 cross 4 general 4 cross 4 matrix, which is a constant matrix, not dependent on space time. So under Lorentz transformation, F will not change. Here, so F is a constant matrix, and since any 4 cross 4 matrix can be written, this 4 cross 4 matrix can be, just a minute. This 4 cross 4 matrix F can be any of these matrix of 16 set of 16 matrices, or they are linear combinations, because this forms a linearly independent set of 16
Yes, yes.
matrices. Okay, because of that. Therefore, this object may not be always Lorentz invariant by itself, but we will see that when F is 1, we know that this term appears in the free Lagrangian of the Dirac field, and this term is Lorentz invariant. When F is gamma mu, gamma phi, these objects, we don't know how it will transform, but we will show. But if it transforms like a vector, then we can multiply. If it transforms like a vector, then it would carry some index u, because then we can multiply it by a mu to make it a scalar. So the Lagrangian will be, the whole Lagrangian will be like this. Okay, if it transforms like a tensor, okay, then we have to multiply like this or some other thing, so that to make it a scalar. It is easy to make scalars from vectors by just multiplying by another vectors, another covariant vector or contravariant vector, as the case may be. But the thing is that whenever Dirac fields will appear in the Lagrangian, they will appear in this form. We will soon study the features about interaction Lagrangians in this class, or maybe in next class. Okay, then we will realize this more. Now, so therefore, it is important that we have to investigate how this object transforms under charge conjugation here, because ultimately we have to see how a total Lagrangian changes under charge conjugation, so that we can associate it with the real, we can compare it with the real physical process whose charge conjugation invariance or non-invariance we can directly see from the experiments. I will come to that. But let us, for the time being, let us postpone that discussion, and let's see how this object transforms under charge conjugation transformation. Clear? Okay. So let's say, so remember, I have written two different Dirac fields here for a particular reason, because when some interactions will happen, it is not necessary only one fermion is there. There can be different fermions. One can be electron, one can be muon, one can be electron, one can be neutrino. So their Dirac fields are different. If they are involved in the interactions, interaction Lagrangian will contain in general different fields. Okay. Let's see. So how this is, for a particular case, psi2 may be psi1. This two and these two fields may be same. Then we have psi bar f psi. That is all. That is a special case of this. But in general, let's investigate this large charge conjugation of this object. Now, charge conjugation of this object, to find the charge conjugation. So let's symbolically write it like this. Under charge conjugation, it should transform like this. Okay, where we know psi c transforms like this, and so this should be psi c. Sorry. And psi c bar, oops, sorry. This is not psi c. This should be psi goes to psi c, and this is psi bar goes to psi c bar, which we have just shown. Okay, so these are psi c and psi c bar. So we have to put it here and check how this object can be related to psi1 and these objects without C. That's called knowing the transformation. So we have to find out this transformation. This is just a symbolic way of writing this. Okay. Now C satisfies this matrix, you know. Now let's write this object. Therefore, this object is, in place of psi1 bar, I have written, use this relation. Okay, this is psi bar, and for psi I have to write this. So for psi1 bar I have written this. I keep F as it is because F is a constant matrix, no particle interpretation in that. Therefore, charge conjugation will not do anything. And for psi2 I have written this. So I mean always note this psi1 and psi2 in the proper place. Okay. Now we can write this as just this is psi1 t C inverse F C gamma 0 t psi2 star. Clear? And for simplicity, for the time being, we will write C inverse gamma FC as a new matrix M. Okay, I will replace it by again this letter, but for okay. So this object M is again a 4x4 matrix because C, F, C inverse all are 4x4 matrices. So their product is also a 4x4 matrix. So look at this object carefully. This object when first object is a transpose, therefore it is a 1x4. Last object is this psi2 star and psi is 4x1. So its star will not change its order. So its star is again 4x1. Intermediate matrices are 4x4 matrices. Okay. Now see that this product of 4 matrices, this object as a whole is a 1x1 object. So this is a single object because this term is a term in the Lagrangian. This is a single object, and this also you can see from here 1x1. The result is 1x1. Now you can write this product of matrices in terms of elements of these matrices like this. Do I need to explain this? Carefully look at this. This is, please tell me if I have done any mistake here. Clear?
It's all right.
Everybody?
Okay, this is okay.
Because this psi1 transpose is the row matrix whose elements are basically psi1, psi2, psi3, psi4. Therefore, it comes here. Don't write transpose here because we have already taken care of by this rowness of this matrix. So now there is a sum over all these indices. All these indices, there are 3 indices, alpha, beta, and delta. They are summed over. Now, since I have written these matrices in terms of their elements, so there is a big sum. So there are many elements here. So alpha runs from 1 to 4, beta from 1 to 4, gamma from 1 to 4. Okay. So truly there are, how many elements? How many elements in this sum? Anybody?
How many elements means?
How many terms in this expression? If you open up this summation sign.
16.
Not 16.
4 cube. 4,
yeah, 64 because there are 3 sums: alpha, beta, gamma. So delta. 3 sums runs from 1 to 4. Okay, therefore there are. So this is sum of 64 terms here. But now, if this sum of 64 terms, which is in the compact form, is written in this way, in every term, this one is an element of a matrix. This one is an element of a matrix, not a matrix itself. Therefore, I can interchange their position because they are pure numbers. It does not dip. So I don't know whether M and gamma 0 will commute or anti-commute or whatever. Will not commute. Okay, but once I write in terms of their elements, I can rearrange them, reshuffle them. Clear? So therefore, because they are elements of the matrix, we can exchange their positions. Also, psi1 alpha, psi2 star delta, they are also elements of row and column matrices. Okay. their positions can also be interchanged. So I can shuffle them as we like, as I like. But now you have to, I am telling you some statement which uh, will be more clear when you start studying quantum field theory. Right now, I am just assume that. So when we quantize these classical fields, psi star, Dirac fields, then after in this, then this field will be quantum fields. In there, this psi 2, psi 1 or psi 2 will no longer remain a 4 cross 1 matrix or 1 cross 4 matrix whose elements are functions of xt. Then it will get the status of operators. So these fields will be operators in quantum field theory. I want to use this here because all this, whatever I am doing, I have to apply finally in quantum field theory. Okay, in the context of quantum field theory. Therefore, if I don't use that, what we will get, I will also show. But if I use that phenomena, that aspect, that in quantum field theory, all these psi's, when fields psi 1 and psi 2, etc., are considered as operators, as will be considered as quantum field theory, even though its components, psi 1 alpha, psi 2 alpha, are single components, but because they will be operators, we have to take care about their commutation or anti-commutation relation while interchanging their position. So if I want to interchange positions of this and this, I can interchange easily with this because this is not an operator, this is just a number. But once this is an operator, once I have to interchange this with this, swap their positions, then I have to take care whether they commute or anti-commute. If they commute, there will be no, it will remain same. If they anti-commute, one minus sign will come. And if they have any other commutation relation, then that commutation relation has to be taken care of. Okay. You got my point. So I am using the fact of quantum field theory, which we have not studied so far, that these fields will get the status of operators in quantum field theory. So since we will apply these results in quantum field theory, then to apply this, we have to take care of the operator nature of these fields, which means when we have to swap this, exchange with psi 1 and psi 2, I have to take care of their commutation or anti-commutation relations. But here, if we take only classical fields, then we can easily swap. Okay, no, we can bring this in front because so far as classical fields are concerned, they are just pure numbers, not operators. Yeah. Is this what I am saying?
Sir, clear.
Okay.
Okay, sir. Okay.
Okay. Now,
Sir,
yeah. Well, yes.
both psi and its components all will be operators.
All will be operators. So psi is defined in terms of its components. Psi 1, say psi 1, psi 2, like this, which are classical fields here. Classical field means they are functions of xt, just functions of xt. Quantum fields means they are operators dependent on xt. All these are operators. All the 4 components will be operators, which means psi should be an operator, but having this 4 cross 1 structure will remain. Okay. So now we are slowly looking towards the window of quantum field theory and interactions. So we are introducing this here at this point.
Sir, why we are going to quantum field theory?
Quantum field theory, because we are going to quantum field theory because the fundamental particles, elementary particles, which interact, they are point particles. So they have the particle nature. But here I am saying, if I say that particle is described by this classical field, the classical field has its effect all through at all x and t. So how we get the localized concept of particles from the fields? These classical fields will not can't give the localized concept of particles here.
Yes, sir. Okay.
Because of that, when we will see, once we quantize this field, take them as operators, then the operators will act on some states which will be particle states. And those states will be these particles, whose eigenstates of this operator, not these operators. We will see that. Here. So when they are operators, they will act on some states, and those states will be, we will see, those states are called quanta, like harmonic oscillator. So what you see, when you say an harmonic oscillator, a classical harmonic oscillator is a particle. Okay. Now you quantize this harmonic oscillator, what you get? You get a wave function, Schrodinger, satisfying Schrodinger equation. Okay. This wave function has its effect all through all at all space time. But the effect of quantization is that you can look at this energy eigenvalue of this harmonic oscillator as n plus of h cross omega. This was not the energy when you have the classical harmonic oscillator. Classical harmonic oscillator have energy p square by 2m plus half m omega square x square. It is a continuous thing. But once you quantize, you get discrete forms of energy. But also you get an idea from here. You are quantizing a single harmonic oscillator, a single simple harmonic oscillator you are quantizing, whose description you get in terms of this wave function phi. But the energy of this oscillator, this quantum oscillator now, this is a single oscillator again, but this quantum oscillator is described by this wave function which has effect at all xt, because it's described by wave function. Clear? So quantum oscillator is not localized at a particular point. That is okay. But its energy, you can write it in this way. This energy you can look, because what is n? N can be anything. N can be 0, 1, 2, 3, etc. So you keep this half h 0 point energy one side, but n can be anything. That means energy of this single simple harmonic oscillator when quantized is equivalent to a collection of n particles, each of whose energy is h cross omega. Clear? Can you say this? Energetically, a quantum harmonic oscillator is equivalent to a system of particles, all of whose energy is h cross omega, and a collection of n number of particles gives you the energy of that oscillator corresponding to En, nth state. Therefore, by quantizing a particle, you get a wave function. Wave function has no localization, but that wave function can be interpreted as collection of a number of particles, so far as energy is concerned. Therefore, these particles with h cross omega, these are not harmonic oscillators. These are just particles. These are called quanta of these fields. Okay. So once you quantize once, so you can see that what you have gained. So you, to start with, you have a single classical harmonic oscillator described by its generalized coordinates q, t, etc. Okay. Once you quantize it, what you get? You basically get a system of many particles which will somehow represent this system in quantum version, right? Therefore, it is the quantization is the way to go from one particle to many particles. It is not breaking up of one particle to many particles. Viewing a system of one particle in a different view like many particles, for that you have to quantize, you have to quantize the system. Now, in this picture, Xi's are all classical fields. They are generalized coordinates representing the fields. At all, you need to know the values of the classical field at all space-time points to get the full description of the field. Now, if you quantize these generalized coordinates like you did for harmonic oscillator, then you will get some idea of quanta of the fields in terms of which you can describe the energy of the system. These quanta will be identified as the fundamental particles. We will see that. So this wave function psi are already result of some quantization. This is first quantization. You go from classical mechanics, you have come to quantum mechanics, combining relativity with it. Now you are doing another quantization, attributing these fields as generalized coordinates. Now you are doing a further quantization, which is also sometimes called second quantization. Once you do that, you will get the concept of quanta in this picture, which can be associated with the description of a field, because fields are localized particles. Fundamental particles are point particles. So quantas are like that. So you can do that, because that is the motivation for doing quantum field theory. We will study this we will see this in great detail when we will study quantum field theory. But since you asked this question, so this is the motivation for doing quantum field theory. In quantum field theory, psi's will be operators. Therefore, in exchanging them, we have to take care of their commutation or anti-commutation relation. Okay.
Sir,
Uh,
you have said that there are n harmonic oscillators. Each energy is h cut omega.
and that n
But
number is not conserved.
okay, but how can we precisely measure the energy? Then the uncertainty in energy and time, this will somehow get.
No. They are free particles. The quantas are free. They have precise energies.
Okay.
Now, anyway, let's come back to this point. I am producing this result in order, keeping in mind that ultimately I am moving towards the domain of quantum field theory, so that I have the results intact. Therefore, I have to take care of their commutation or anti-commutation while swapping psi's. Okay. But so far as this discussion is concerned, if you don't look at quantum field theory, if they're pure classical fields, you can exchange them because they are just matrix elements. Fair. But we are taking care of their anti-commutation or anti-commutation relation. Now, this is a result, again, I will state, which will be soon be proved in quantum field theory, in study quantum field theory, is that when the Dirac fields become operators, that is quantum field, when you do the quantum version of Dirac field theory, quantum field theory of Dirac fields, then we will see that these operators, psi1, psi2, etc., will become anti-commuting operators. This I just make a statement. I will show, we can show this in due course. Okay, so don't ask me to show, because I just making this statement because let me say this because why they will become anti-commutation operators? Because of the reason that fermions obey Pauli exclusion principle. That is an translation of this principle in terms of operators. We will see this. So we are using this result that fermionic operators in quantum field theory, Dirac fields, when become operators in quantum field theory, they always anti-commute with each other, any other field, also with itself. Okay, if a field anti-commutes with itself, means psi is equal to 0. That means two particles can't be at the same state. So this interpretation you will see later. But for our discussion, I just borrowed these ideas for Dirac fields, and we will use the fact these fields are anti-commuting fields. That means when we exchange their positions, one minus sign will come in the front. Clear? Therefore, clear means these things will not be clear because I have not discussed it, because Sanjay will discuss it, or I will also discuss it in due course. Okay. So keeping this in anti-commutation relation nature of quantum Dirac fields in mind, we write this as So this object, which we were written like this, now we swap positions. So what we do, we bring this in the front and take that at back so that we will get a minus sign, because I take the deduct fields to be operators and their anti-commutation relations should be there because they are deduct fields. I borrowed that result. And also because these matrices I interchanged, because these are just matrices, I can always elements of these matrices, I can always interchange their elements. Okay. And now again you can write, this is again this is 64 terms. I have just rearranged them so that I can write it again. So far as this index is concerned, the indexes are written in such a way that I can again write it in terms of just matrices like this, because obeying the matrix multiplication format of these indices. Okay, so this will be, so this should be transpose. So this should be psi2 star transpose, psi2 dagger. This is gamma 0, this is mt, gamma 0 into mt, this beta beta same, and this again mt into psi1 alpha alpha same. Is this clear?
Yes.
Everybody?
Yes, sir.
Therefore, I can write psi2 dagger gamma 0 is psi2 bar. So I write this empty. Okay, therefore, now look at this term where we started with. This was equal to minus of this thing. This was equal to minus of this thing. So this thing. So with this minus will go. So this will come. And now I replace M by this C inverse FC. Okay, this F was there. M was intermediate state, I introduced M. So I replaced it. Therefore, I can say this object under Church conjugation will transform like this way. When psi2 and psi1 are quantum fields, if it were classical fields, there would be an extra minus sign here, right? But I am not taking this minus sign to confuse for you, because ultimately we are doing this all for quantum field theory. Therefore, for this Church conjugation, we will not study any classical field theory anymore, since we are at the doorstep of quantum field theory. We are introducing this result. Clear? So let me take a break for a minute or 2 minutes. Hello? Okay.
Yes, sir.
So all of you are keeping good health. So all of your health is okay. I am asking everybody. Do you know?
Yes, sir.
Yes, sir.
No, because the season is changing. That's why I'm asking.
I have viral fever. I had.
Okay, I take care of you because if you have poor health, you will not have a good mind, so you can't study physics. Anyway, okay, so let me proceed. So we have seen that this object under charge conjugation transforms like this. Look at this object very carefully. Just stare at it. That's why I left it here. The charge conjugation swaps the position of fields psi1 and psi2 here. You will not recognize it if both are same fields. Like you remember when we did parity transformation of say psi1 gamma, say something gamma 5 psi, say f is say gamma 5. If I do, when we did parity transformation, we take the same psi. Now if you take two different signs and do a parity transformation, you will see that psi1 will transform like gamma 0 psi1, psi2 will transform like gamma 0 psi2. Sorry, psi1 will transform, this will transform like something, this will transform like something, but this will never change the positions of psi1 and psi2, whatever it may be. So you know that under parity this transforms as psi1 bar minus gamma 5 is 2. But under C, this will, we will see how it transforms under C, because this is also not F. This F changes to this. This is different from F. But the thing is that this charge conjugation transformation swaps the field positions. The psi1 bar becomes psi1 on the right side, psi2 becomes psi2 bar on the right side. Also, this constant matrix takes a different form by this transformation. The charge conjugation transformation is not that simple because it is dealing with internal degrees of freedom of the system. Parity or Lorentz transformation, continuous transformation, they deal with space-time transformations. Okay. Also, time reversal deal with time transformations, which we have not discussed yet. But charge conjugation is a bit complicated. When it is applied on for Dirac field, it is further complicated because Dirac field has its own complications or structures. But complications have their different structures. So two complicated people you put together in a room, anything can happen. You don't know how can happen. So you have to thoroughly examine what is going to happen if you put two complicated person in the same room or in the same table for discussion. Okay. Now we have to actually see what does this mean. So we have derived this equation, derived this transformation. Now let us check case by case. Say when f equal to 1, then we are looking at charge conjugation transformation of this object. You put f equal to 1 here, so this will transform to f becomes 1, so it becomes C inverse C over transpose. C inverse C is identity, whose transpose is also identity. So you get psi2. Okay. Clear? So this object and this object are not same. They are 1 and 2 are swapped. Okay. Now So if you want a Lagrangian which is containing psi1 and psi2, which should be invariant, and if you demand that your Lagrangian, you want your Lagrangian to be invariant under charge conjugation, then if your Lagrangian contains a term psi1, psi2, it will not remain invariant under charge conjugation. The Lagrangian should also contain this term together, so that under charge conjugation, this term becomes this and this term becomes this. As a whole, the Lagrangian remains invariant. Clear? In principle, you can add some constants alpha and beta here. If alpha beta are different, then also, even though the two terms are there, this will not remain invariant. This whole term is not invariant under charge conjugation, because this term will become this, but alpha with alpha. This term will become this with beta, so which are not equal. So alpha and beta also has to be same, these constants. Okay, so we will see this later when we will construct interaction Lagrangians, but you have to do. I tell this because at that time you will see the beauty of charge transformation. Okay, now when f is gamma 5, you see its charge transformation, put gamma 5 here. Now we have proved this property already, property 1, C gamma 5, C inverse gamma 5, C is gamma 5 transpose. So this thing in the bracket should be gamma 5 transpose, and there is a whole transpose above, which makes it gamma 5. So this also transforms in this way, where fields are field swap. Okay. So this is also not invariant under charge conjugation. And which is justified because Dirac field represents fermions, its charge conjugation can't be same. Their particles and antiparticles are different. Okay. In that sense, it is also desirable. Now come to, if f is gamma mu, okay, if is gamma mu, then this, okay. Now you know C inverse gamma mu C is minus gamma mu tau, so put minus gamma mu tau, and there is a minus gamma mu t, and there is a whole t above, which makes it gamma mu, but with a minus sign. So this object transforms like this way under charge conjugation, where you get a minus sign extra with respect to this kind of objects. So there is a minus sign, also there is flip. Okay. So if you have to construct a Lagrangian out of this two psi1 and psi2 involving gamma mu terms, like this kind of terms, then you have to take difference of this. What you have to take, because, can you tell me? Psi1 gamma mu psi2. If you take the difference, will it remain invariant? A minus sign will come in the Lagrangian. If you take the difference, if you take the sum, what will come?
One minus sign come.
If you take the difference, what will come?
Remains invariant, I think.
You take the minus sign, this will become this. But
yeah.
So this will become minus of this. Okay. But this will become minus of this. So sign changes or not?
No, sign, I think not. So.
Is this
Sign,
under charge conjugation transformation? Is there this relative sign difference between these two terms?
psi 1 bar gamma mu psi 2, this becomes minus psi 2 bar gamma mu psi 1, and minus psi 2 bar gamma mu psi 1 becomes psi 1 bar gamma mu psi 2. Then this becomes invariant.
Okay.
Under charge conjugation.
If you take the plus sign,
then there is a relative minus sign.
okay.
Total.
So So you have to be careful while making charge conjugation invariant objects out of this kind of terms. Okay, but if you require that your final Lagrangian should violate charge conjugation, then you have to take willfully this plus sign here, or you can take alpha, beta, with minus sign. You can also take when alpha, beta are different. Okay, so this kind of arguments we will use later when we make use of these objects while constructing interacting Lagrangians. Interacting Lagrangians will be studied for our purpose because we are studying particle physics and all particles do interactions. That's why we are studying these objects. Now, if gamma mu is f is this, then the object f is this. Its transpose, you introduce C and C inverse in between here. Okay, so this object is, by definition, this is minus gamma mu tau, and this object is simply gamma 5 tau. So minus sign you bring in front. So take the whole tau. So gamma 5 tau over. So this will become like this. Obvious. So this will remain. And this, you know, these anti-commutes. Gamma 5 anti-commutes with any gamma mu. So you can flip their positions. Flip their position, anti-commutes. So the minus sign will go. Okay, so this will become positive, but signs on. So these things are interesting things. Gamma mu, the sign swap, the sign changes. This thing does not change. We will see how this kind of objects will be will give us useful way of constructing Lagrangians, particularly for weak interactions, where charge conjugation is not always respected. We'll see that anyway. So this is what we have done. Okay, now come to the third part, which is the charge conjugation of electromagnetic field. We have done charge conjugation of real scalar field, complex scalar field, Dirac field, now electromagnetic field. You see, Lagrangian for this electromagnetic field is this, free Lagrangian. Now, this free Lagrangian for this electromagnetic field, the equations of motions of the field are this. These are Maxwell's equations in vacuum, because this is a free field. It is not interacting with any charges. Now, where f mu nu is an antisymmetric tensor having 6 independent components. We discussed this earlier, you also know this. And 6 independent components of f mu nu are the 3 components of electric field and 3 components of magnetic field, which you can write like this. Because F01 is E1, F02 is E2, and Fij is F12 is minus V3, F23 is minus V1, like that. Okay, so there are 6 components, all are electric field and magnetic fields. Therefore, electric field and magnetic field are physically measurable quantities. Components of electric fields and magnetic fields, and they are real numbers. Therefore, f mu nu is real. Clear? And since f mu nu is real and it is connected to m mu nu by this difference, by this relation, you can simply say m mu nu should also be real. Therefore, m mu nu is a field where A0, because you know A0 is the scalar potential, vector A is the vector potential. They are real vectors. Clear? Their components are real. They are real things. Because this is real, the field should describe particles which are their own antiparticles. That's the reason. Their electromagnetic field represents the particles which are the photons. So we will see later that once you quantize this electromagnetic field, it will become an operator whose quanta are called photons. This is the relation between field and particles. We will see that. But the thing is that since they are describing these particles, and since this is a real field, this particle should be their own antiparticle, because charge conjugation operation we associate always with the complex nature of these fields. Okay. Now there is a catch, small catch here, or very now you will slowly, I am moving towards interactions in the context of electromagnetic field. See, since electromagnetic field, this Lagrangian, free Lagrangian, contains, is quadratic in F. Okay, F mu nu occurs twice, and F mu nu is this. So you can check that both A mu and minus A mu correspond to the same Lagrangian. Okay. If you change the field by its minus sign, overall minus sign, without changing x, okay, you are not doing parity transformation. Parity transformation means changing vector x to minus vector x. You are just changing the field to minus mu nu without changing x and t. So at a particular point, electromagnetic field is in some description. It is given by this. You write down its Lagrangian. If someone takes this field as this electromagnetic field, say B mu as this, then this B mu field will satisfy the same Lagrangian equation, same free Lagrangian. Will have the same free Lagrangian because it is quadratic in F. Therefore, this minus sign will go. Because of this minus sign, F will change sign, but it will be quadratic, that minus sign will go here. Therefore, from free Lagrangians, you can't distinguish between what field you have to choose to describe a free Lagrangian. You have a degeneracy of this, even this four vector, but the simple degeneracy of this plus minus degeneracy. Okay, these two things can represent the same electromagnetic field. Okay, that I have written here. Or you can say the electromagnetic Lagrangian is invariant under this transformation. If you take it to minus mu, it will remain the same. Plus mu means no transformation. Okay. Now,
hello, sir. Sir, how is it related with spin? I mean, in Klein-Gordon real scalar field, photon was not there because of its spin, and now photon is related to mu. So, how does it
spin, I have not related spin with the complex nature of the field. I have not related spin with anything. I have related all intrinsic quantum numbers except spin. Electric, all the charges, Q, electric charge, lepton numbers, baryon numbers, etc. These we have called charges. If you look at this, my previous note, you can see that I have carefully called charges to all these quantum numbers and not spin. Spin is related to some other thing which I have not discussed here. It has a Lorentz invariance property also. It is not as simple as a classical field has no structure other than simple space-time dependence which remains invariant under Lorentz transformation. This field, Dirac field, has a rich structure, but mu field also is real, but it has a structure in the sense it is a four-component object. Somehow among this I can use these multiple components to accommodate the spin of these particles. We will see that. But so far as electric charge is concerned, electric charge is always, so far as all the intrinsic charges are concerned, other than spin, they are related to, all these properties are related to the complex nature of the field. Since mu is real, so whenever a field is real, you can say You can't say whether it will be spinless or not. You can say that it will have, it will be its own antiparticle. Its charges are zero, all its charges are zero, not spin. When it is a real as well as scalar, then it has no structure at all. It is real but not a scalar. In that sense, it has 4 components. Okay, this four components of a vector. So I have something in theory to which I can relate the spin to, but for real field which is scalar, which is a single function only, single function of x and t. It is just a function of x and t. There is no structure associated with this x and t. Just with an x and t, I relate a simple number with a particular position. I associate a single number. A single number cannot represent different states of spin. But here there is not a single number. There are 4 numbers. So it may be possible to describe spin by these numbers, different spin components by this number. Like photon has a spin 1, if you know, measured spin 1. So it can have spin components 0, 1, -1. They can be described by these 4 things. We will see that. Okay. But so far as charges are concerned, photon is its own antiparticle. So, and this is also real. So I have associated all these charges to intrinsic charges, which is electric charge, electron number, baryon number, all other numbers like color, strangeness, etc., to the charges. Any field which is real, whether immaterial, whether it is a scalar or a vector field, so far as it is the real, it must describe particles which are their own antiparticles. If it is real and also scalar, it will only describe particles which are antiparticles which have 0 spin. If it is not a scalar but real, then it can represent, it can represent particles with spin. Okay.
Yes, sir, but how spin is related with
that I have not shown, but that we will show. That how spin is related to this mu, how mu describes a spinful particle, how Dirac field is spinful particle, and how psi describes a spinless particle, that has not been explicitly shown in this course yet. We have only intuitively said that since scalar field doesn't have any sort of structure, it is guaranteed that it will not describe any spinful particle. That comment we have only made. To show exactly that Dirac field represents spin half particle, mu represents spin 1 particle, we have to do something more. I have not done that yet.
Okay, sir. Okay.
Okay, this will be done. Next after Kali Puja, we will show you how Dirac field represents spin half particles and how mu can represent spin 1 particles. Then you will understand this. But right now I am using our intuition, basic intuition, that a scalar field containing no structures should no way represent any particles carrying charge or spin. But mu, though it is real, it is not complex, but it has 4 components. Because of that, I can't say that it should not represent spin, but since I have already associated charges with complex nature of the fields, therefore I can say since mu is real, the particle it represents must be chargeless particle. Chargeless means all quantum numbers should be 0. For photon, all quantum numbers are 0. For spin, I can't say what it is spin from this intuitive argument. I can at least say I don't know what will be the spin of this particle. I can surely say that its spin should be 0 or non-zero. For scalar field, I can surely say because it has no feature at all. Mu has some feature. Some feature means it has 4 components which transforms in a particular way under Lorentz transformation. Okay.
Yes, okay, sir.
Okay. Now, look at this very carefully. When electromagnetic fields interact with electric charges, okay, electric charges which carry charge density rho and current density J. So there you have an electromagnetic field, and electric charges are objects, external electric charges, which are objects external to the field. You put this, that charge is not in the description of the free field. Mu is a free field which satisfies which corresponds to this Lagrangian or satisfies the Maxwell's equation in vacuum. Now you put electric charges inside in vacuum. In vacuum you have electromagnetic field. Now you put electric charges and you pass currents through vacuum. That means you are introducing a charge density and a current density in general at every point in space-time. That means you are introducing a 4 J mu at every point. Therefore, now the Lagrangian of the whole system, now the whole system means the electromagnetic field as well as the charges and currents which are external to the field. So this Lagrangian of the whole system, in the whole system, what is there? You have this free field, okay? Mu was a free field. Now it is interacting with you. Now you know this is the Lagrangian of the electromagnetic field in a medium, or when charges are present, when J mu is the current. Clear? This part of the Lagrangian you can think of as the interaction Lagrangian, because mu is now interacting with the charge densities and current densities. This charge density and current density may be originated by motion of charged particles which are external to the mu. Okay. Yeah. So you have the free Lagrangian plus this interaction Lagrangian gives you the total Lagrangian of the system, which is your system is now the electromagnetic field mu itself as well as the charges and the currents in the system. So this comprises the whole system. Then this Lagrangian, when put in the Euler-Lagrange equation, satisfies this equation, which is the Maxwell's equation in presence of rho and J. Maxwell derived this, experimented this, and found this long ago. We all know this. This is Maxwell's equation. This is the same equation, delta dot E equal to rho by epsilon 0, like that. Rho and 0 are non-zero. Rho and J are non-zero. Clear? Clear?
Yes.
Now, let me read out so that in case of interacting electromagnetic fields, fields are now interacting, the system contains the field mu, the electric charges and the currents external to the field. Now, when one thinks of flipping the charges of the system, entire system, whatever is now in your system, whatever is now in your system means you have the electromagnetic field, you have the external electric charges and currents. Now, external electric charges and currents are produced by motion of charged particles in your electromagnetic field. Now, suppose you are doing a charge conjugation of the entire system. That means you have to take the charge conjugation of this field mu. Okay, that means you have to make the particle which is represented by mu its antiparticle. That means you have to make photon its antiparticle, and you know photon is its own antiparticle. Mu being a real field, it is its own antiparticle. Therefore, the charge conjugation of mu's appears to remain, do nothing to mu. But once you do the charge conjugation of the whole system, the charges and these external, the charges and the currents which are produced by some motions of electric charges and motion of electric charges and static charges, when you flip the sign, those charge density and charge and the current should flip sign, because you flip the sign of a charge particle, the direction of current gets changed and the current density magnitude also gets negative if you change it to a positive to negative charge. Clear? So we can safely say, this this object, whatever it may be, under charge conjugation, under changing all, flipping all the signs of the charges, which results this J mu, under that flipping of sign, J mu will change sign. Is this clear?
Yes, sir.
Therefore, look at this now. Just I said, we have seen that free Lagrangian, this free part of the Lagrangian, which is purely consists of A mu, no J mu, no J mu is there, is always invariant or insensitive to this interchange. This fact you can write in this way also if you wish. Under charge conjugation, A mu of x either remains invariant or it can change to a minus of this. It is real, so no star will be there, but even if it changes minus sign, you can't distinguish between the Lagrangians. That satisfies the fact that photon will be its own antiparticle. Okay, but theoretically, A mu and minus mu can represent the same photon because it has the Lagrangian which is quadratic in free Lagrangian, which is quadratic in F mu nu. So technically, we can think that charge conjugation changes A mu to either this or this, so far as A mu is a free field. This, so far as invariance of free Lagrangian is concerned, we can think these changes, because this is not a transformation of coordinates. We have just a simple freedom of changing the structure of the field. Here structure means by introducing this minus sign here, because there is a place here where I can take plus or minus. Because doing that, I can make the fields different, and we can't distinguish between the real fields. We can distinguish between the Lagrangians from these two fields. So in principle, I can say technically that charge conjugation takes it to this or at least to this. Okay, so these are general statements. So in general, charge conjugation can take mu to this, or also we can take this as a charge conjugation transformation without any loss of generality, because both will give you same free electromagnetic Lagrangian, which is our requirement, that all free Lagrangians are invariant under charge conjugation. This transformation does not violate that, and this transformation also does not affect space-time anyway. So this transformation can only be linked to charge conjugation, which deals with internal things. It is just multiplying it with a minus sign. Clear? Is this argument clear? This is a very tricky argument.
Yes,
Sir, but will it be effective for interacting
Yes,
when
that's
mu
why I'm
mu
saying.
comes?
Yeah. That's what I'm saying. Now I am stating an experimental fact. The fact is that the one thing is that this effect of free Lagrangian is never observed, because you only observe interaction. So whatever be the free Lagrangian, you can't observe. That means you can't distinguish from free electromagnetic field which one is actually accepted in nature. Okay. Now, what is observed is that all electromagnetic processes, you mean, I discussed in the early stage of our course, which have an ordinary time scale of -16 seconds. They are invariant under operation of charge conjugation or particle to antiparticle exchange. So this is a statement, this is an observation. So what is the meaning of this observation? For example, if you measure the cross section of this process, positron scattering with some energy of this positron and this positron, energy and momentum, and you measure the cross section of this scattering, where you just consider this scattering which obtained by flipping the signs of all particles here. Then you will find that these two cross sections are exactly equal. Nothing changes. These two cross sections are exactly equal when all these electrons and all these positrons, the energy and momentum of these electrons and positrons are kept intact. So if this has a energy momentum P1, this has also a momentum P1, this has a momentum P2, this has a momentum P2. You only just flip the charges without changing anything. Momentum, energy are not intrinsic charges. Or you only change the intrinsic charge, you will find the measured cross section at that energy will always be equal for these two scattering, also for this scattering. Electron photon scattering in the laboratory, if you measure the differential cross section even at given energies of this, at the same energies of this is true for all electromagnetic processes, which we can generalize by saying this statement: all electromagnetic processes are invariant, means any measured quantity about an electromagnetic process will never change if you just flip the intrinsic charges of all the particles without changing any other thing, not position, energy, momentum, etc. Clear? This is an observation. That electromagnetic processes are invariant under particle-antiparticle exchange or under charge conjugation. Is this clear? Is this clear?
Yes, sir.
Yes.
Now, since all physical processes are related to interactions, these are all physical processes, so they should be related by interaction Lagrangians, not free Lagrangians. So somehow you will see in latter part of this course, maybe particle physics 2 course, how I can calculate the cross section which we have already defined, differential scattering cross sections in quantum mechanics, in particle physics also, how we can calculate it from a given interaction Lagrangian. So if L int is given, you can uniquely calculate sigma. That is called the Feynman calculus. We use that. But in this calculation, free Lagrangian will never come. We will see that. So, but since they are interactions, they must be related to interacting Lagrangians. That we can intuitively say. Therefore, so we can state that the fact that since all electromagnetic processes are invariant under charge conjugation observationally, therefore all interaction, this interaction, electromagnetic interaction Lagrangian must also be invariant under charge conjugation. Yeah, that means under charge conjugation, L int will remain L int. Here, this statement I can make only after I observe that all electromagnetic processes are invariant. Clear? Now, let us write the total electromagnetic Lagrangian. Now, we should say that our assumption that L free part is invariant under C, that gives us two possibilities, this or this, mu going to mu or mu going to minus mu. Both can be equivalent descriptions of the charge conjugated, this free electromagnetic field. But observation says that L int remains L int. That means if you take the first possibility, then mu changes sign. Mu does not change sign, so this will not change sign. This will also, mu will not change sign. But you know that J mu changes sign under charge conjugation because it is a current. So if current charges are flipped, J mu will change sign. Therefore, if you take this possibility, okay, so what will happen? If you take this possibility, you can write it like this way, say L int is this, Therefore, in place of L int is this. Therefore, charge conjugated L int will be like this and this, which is basically this. So this equation will be satisfied because J mu charge conjugation is minus of J mu. Therefore, you can say A mu must be equal to minus of A mu. If A mu C is equal to plus of A mu, then this equation will not hold, meaning this Lagrangian will not remain invariant, interaction Lagrangian, which is an observation. So observation selects out of these two possibilities, which followed from these as a assumed invariance of free Lagrangian. The observation selects out this possibility, the negative possibility. So we can say now that electromagnetic field under charge conjugation, if you take care of the phenomenal world, the visible world, then you have to assume, you have to take that this is the charge conjugation transformation of electromagnetic Lagrangian. Any questions?
There should be a minus sign. Please scroll up.
There is a minus sign here.
No. Please scroll up. Here, yes.
Where?
Right hand side, minus J mu mu.
No. Here, in this equation.
Yes.
No.
In the right hand side?
Right hand. No, this minus sign cancels. L int itself is minus of J mu mu. So this I have written just in terms of these conjugated objects. Now this minus and I can cancel. So therefore we have these equations. Now you can see, now in place of J mu C, you put minus of J mu in place of this. If you put minus of J mu, then A mu C becomes minus of A mu.
Okay, I get.
So, sir, does it mean photons would have some kind of charge?
No. A mu is always real. Charge is always, electric charge is always charge, or any other intrinsic charge is always associated with the real nature or complex nature of the field. Multiplying it by minus doesn't make it complex. So it is still real. But out of these two possibilities, plus mu or minus mu, it will be minus mu. It doesn't mean anything to photons. Only thing is that in theoretically, photon field will transforms under charge conjugation in this way, which keeps free photon Lagrangian invariant. But interacting Lagrangian also invariant, because that is the observation. So photon interacts with charged particles in such a way that its field should transform under charge conjugation in this way. This does not attribute any intrinsic properties of photon, because all intrinsic properties of photons are associated with charges of these complex nature of the electromagnetic field, and since electromagnetic field is real, all intrinsic charges of photon are zero. Applying this minus sign just differentiates how photon will interact with charges and currents, rho J mu. Electromagnetic field will interact with J mu. It can interact in two ways: mu going to mu or mu going to minus mu, both ways. But observations shows that it can only interact when mu is minus of mu. So we can say now the photon is represented by an electromagnetic field which interacts with other charges and currents in such a way that electromagnetic field under charge conjugation should transforms like this way. Okay. So this is, a trivial transformation, just multiplying it by minus sign without changing the structure of anything, without changing the real to complex. Okay. So that internal structure has inherent, is intact. Clear?
Yes, sir.
So now we summarize before ending today's class. what we have done so far, look at a bird's eye view in 2 slides. So we have studied 3 kinds of transformation so far. Lorentz transformation, which is a continuous transformation by this matrix. Parity transformation, which is this transformation. And charge conjugation transformation, which is this transformation. All intrinsic charges are made negative, okay, or particle to antiparticle. Under these 3 transformations, we have seen how the different fields transform. So if a real scalar field under Lorentz transformation does not change, so it is a scalar. Okay. Now under parity, it can change to plus minus phi of x tilde. X will change because x tilde is now t of minus x. Under charge conjugation, I have shown you it will not change because it is real, but you still here you can add that freedom also. I have not told you while telling this, while doing charge conjugation of real field. You can add because the free Lagrangians are quadratic in fields, therefore this will not change. So charge conjugation of real field also, it can, both possibilities are there. For the same reason for electromagnetic field. Okay. But it has nothing to do with spin or intrinsic charges of the system. For a complex scalar field, Lorentz transformation keeps it invariant, same. Parity transformation, space inversion, changes the field, this argument to x tilde, and you can add, since it is complex, you can add a eta p is a phase e to the power I theta terms, a phase to it. So this will keep free Lagrangian invariant. Okay. So all these transformation properties of the field that are derived from assuming free Lagrangian of the corresponding field remains invariant under all these transformations. Okay. And just a minute, I have a phone call I have to receive. Hello? I am taking my commitments. Bobby, I don't know. I have sent them the attendance sheet at the first class. Yeah, because I have taken, because they have given these numbers. Okay, so I am in the middle of a class. So, okay. Hello? Okay. So, similarly, this for complex scalar field, under charge conjugation, it changes to star. So, keep a careful look when fields are complex or not real, their charge conjugation will star it. Similarly, for mu field, you can see these 3 transformations. The mu under Lorentz transformation, it is a vector, so it will transform like the coordinate. Under parity, we have seen that it may transforms like this or transforms like this. We will later see that some observations will select this out. We will later see, but let's not talk about this for the time being. Also, the mu field under charge conjugation, you can, in principle, take it transforms like this way or this way, where this one is selected by observation. And this complex psi field, which under Lorentz transformation transforms like this, where S is this. Under parity, it should transforms like this. Gamma 0 is there, and eta p is a phase. Under charge conjugation, it should transform like this. So this is the whole summary of this class, of these classes. So just when we, for our next classes, just you have to keep this page in front of you. I mean, because we will use these results. So I put all these results in a single page. Also, there are terms here like psi 1, psi 2 bar. Okay, this object does not transform under Lorentz transformation. You can check. and under parity it's like this. Under charge conjugation, 2 and 1 flips. Okay. Now, because anything which does not change under Lorentz transformation, we call a scalar. So it is called a scalar. Now this object with gamma 5 remains invariant under Lorentz transformation. It takes a minus sign under parity transformation and remains this under charge conjugation. Anything which does not change under Lorentz transformation is a scalar, and which flips sign under parity is called pseudo. So it is called a pseudo scalar. Okay. So it is a normal scalar, no name for that. It is a pseudo scalar. Similarly, this object, you can check that under Lorentz transformation, it transforms same way as the coordinates. Therefore, it is a vector. And under parity, its space part and 0 part and I part transform separately. You can check previous class notes. So space part, time part remains same, space part flips sign. Okay. It's a vector. And under charge conjugation, 1 minus sign comes and 2, 1 and 1 are swapped. And this also, this same result with a no minus sign here. And this is also a vector. But under parity, with respect to this, time part changes sign, space part does not change. If space part of a vector does not change under parity, we call it an axial vector. Okay, like angular momentum is an axial vector, all of you know. Under it is an axial vector. Linear momentum is simply a vector, or you can call a polar vector. Because if you change r to minus r, p will change to minus p, because p is ddr of ddt. But if you change r to minus r, p will also change sign. So L will not change sign. So L is an axial vector, p is a polar vector. In that same sense, this is called a vector, this is called an axial vector. Or pseudo vector. Pseudo is also a name for axial. This is called a pseudo scalar. This is a scalar. Clear? So let me stop here. You can ask any questions if you have.
Sir, in our whole discussion, why in Dirac bilinears, why we are omitting the sigma mu nu?
Oh, I have not written it because you can calculate it. I have skipped it because see, there is no reason for that. The thing is that see, if you know this, it is very easy to calculate sigma mu nu. That's why I have not done that. Because once you know how this object transforms under charge conjugation, then if you put sigma 1, sigma mu nu is basically a commutator of sigma mu sigma nu. So basically you have to find out how this object transforms. Okay. And then you can know how to do this.
Yes. I think I don't think.
Try at home.
Hey, yeah, this is okay, but is there any physical reason that?
No, not that much. Generally, these things does not appear too much in the Lagrangians we will encounter. This Lorentz transformation is a tensor. We will see that if you do the Lorentz transformation, it will be like lambda mu rho lambda nu sigma into same thing with rho sigma. It is a tensor, and therefore if it has to contain in the interaction Lagrangian, it has to be multiplied by two vectors, two kind of vectors. Right now we have only one type of vector here, mu. We'll see. So this is a Lorentz invariant term which can be a candidate for a Lorentz invariance Lagrangian. Okay, there is no harm in that. But there is no physical process which is represented by this Lagrangian. We know. The physical processes we know. Only three kinds of processes we know: strong, electromagnetic, and weak. They are not represented by this kind of dimension. These are theoretically they can represent some processes where some new particles you model in your model. You consider some new particle which you want to study theoretically. For that, this may be useful. Okay, so that's why I skipped it. But in general, it should be there.
Okay, sir. Okay.
Okay, so let me stop it here. Thank you. Any other questions? When is my next class? When is my next class?
Thursday, 3 p.m.
Okay, let me see. There is a 50% chance that I may reschedule that class, but let's see. Do you have any class on Friday?
Bobby sir's class from 3:30 and if
Okay, let's
no,
see. Let's see.
Bobby sir's class,
Okay,
Samik sir's,
okay, okay.
I think
Leave it. Shamik sir is he taking class now?
no.
So not till now.
Okay, okay. Okay,
So,
so
is there any news of university opening in December?
no, I don't know. I don't know. There is a possibility. There is a possibility that we had some discussions, but very premature discussion with the office, the authorities, that maybe some if things remains normal after train runs and etc. After a careful investigation of the situation, you may be called in the university to stay for those who are the hostelites for 10 days so that you can complete your labs, previous year's lab course. Some experiments you have to complete, and then we will see. Then because no student for other departments there are no students are there, so they want to put you in hostels in keeping the distancing, social distancing. So maybe one boy in a room, like that. And those who commute daily, they can commute daily. But that depends on how the train functions and what the situation is. So there is nothing final. So we are thinking like that. That's why I asked you how many of you live in hostel like that. But I got no idea from the university. No information from the university. Whether no one can say anything right now. Let's see. And so far as my reading is concerned, I mean, it will not open. No one told me this, but what I sense about the situation is that it is difficult that when in December we can meet physically. I'm not sure. Okay, no one can do anything about this.
Okay.
Okay, so see, I am teaching first year students. I have not seen them even once. So I don't know how the teaching is going. You people I know because I know in what way of talking you will understand things. But for the first year, I have not interacted. None of the teachers have interacted with them at all. So anyway, so leave it for the time being.